I'm going to be talking about another photoelectric effect problem. This one's a little different than the last one that I went through, but it uses all the exact same concepts. To start this off, note that we are told as our first statement of this problem that the threshold wavelength for emission from a metallic surface is 500 nanometers. What does that mean? Well, let's imagine our metal surface here. And let's note that any values that are given as threshold values really relate to the properties of the metal itself, which means they're going to relate to the work function. Because you'll notice the very first question here is, what is the work function for the metal? So when I'm told that that threshold wavelength of 500 nanometers is what the property is for this metal, that's going to allow me to calculate the work function. So anytime you see threshold, remember that that's a property of the metal. Now, how we want to visualize this is that by telling us that the threshold wavelength is 500 nanometers, it's telling us that if we take light coming in and striking the surface of 500 nanometers, which means its wavelength would be 500 nanometers, that we are going to get an electron ejected, but that the velocity of that electron is going to be 0 meters per second. Why is that important? The reason the velocity being 0 is important to note here is because we do not have any kinetic energy involved in this particular process that's being mentioned in the first sentence of this threshold wavelength, right? All this is telling us is that light of 500 nanometers basically has the exact amount of energy that we need to get an electron to eject, and no energy is going to be left over. Okay, so if you haven't watched my first example video, on a photoelectric effect problem, I'd encourage you to go back and watch that, because that one's kind of a little bit more of the full picture of what can happen when light strikes the surface of a metal. We're going to talk a little bit more about that full picture eventually here, but I think it's important to have kind of looked at a normal situation like that before you try to apply it to kind of the multiple different situations that we have happening here, where there's multiple different wavelengths being mentioned in this problem, right? So we have to know how to think about light of different wavelengths striking a metal surface. Now, if you go back to that video, you will note that I showed a relationship here between the three colors that I have in this diagram here. Basically, the light coming in has some energy. The electrons being ejected from the surface of the metal can have some kinetic energy if they're moving with some velocity. And the metal itself has this binding energy, this work function, which is the energy that's required to eject an electron. Now, when we put all three of those energies together, in the previous video, I mentioned that the energy of the light coming in basically sets the total amount of energy available in the problem. And that energy, which is in each single photon that light has, that energy gets transferred from the photons coming in to an electron in the metal, and all of that energy goes to the electron. So for each photon that strikes the surface, all of its energy goes into one of the electrons. And then that electron uses that energy for two separate things. It uses it to eject from the atom, which is the energy that's represented by the work function or the binding energy. And if there's any energy left over, then that's where the kinetic energy of the electron comes into play, and that's where the velocity comes into play. So if the energy coming in from the light represents all the energy we have available, and that energy is going to go into these two pieces, right, the work function and the kinetic energy, then really what we're saying is that the energy of the light is equal to the work function plus the kinetic energy that the electron's going to have if there's energy left over, right? So the important thing to remember here is this kinetic energy amount is the leftover amount of energy after we've paid up the cost of getting that electron to eject, right? Which is the work function, right? The work function is that cost to get the electron to eject. So in this situation that's being implied with this threshold wavelength, when you see the word threshold, you want to remember that that refers to a situation where the electron is ejected, but it doesn't have any velocity. So in that case, right, if the electron has no velocity, then we don't have any kinetic energy, right? There's no kinetic energy in that situation. And this equation then becomes the energy of the light is going to be equal to the work function. But we have to remember that this is only when an electron is ejected with no velocity, right? No velocity. Okay? So you can basically why I'm really trying to hammer this point down is because this equation often ends up being the one that people want to use for all of the photoelectric effect problems. And it's an appropriate equation to use in certain situations, but you have to know when those situations occur. So what I'm trying to tell you here is the only time you can use this equation is when you know that you have light striking the surface of the metal, ejecting an electron, but that electron has no velocity. And typically, as we said, this situation will be indicated by the term threshold, right? If you see threshold wavelength, threshold frequency, threshold energy, anytime that term threshold is used, that's referring to this specific type of situation. Now, keeping this in mind, right, how are we going to use this to solve for the work function? Well, remember, this energy of the light, that's just an equation, and we saw this in class. It can be hc over lambda, so if you're given a wavelength, you can use wavelength to calculate the energy of the light. But remember, you can also use the version of this equation that looks like this, where it's h times nu, right, h times frequency. So if this problem gave a threshold frequency instead of a threshold wavelength, then you would just use h nu to calculate the energy of the light. But since we're given a wavelength here for the threshold value, we're going to use hc over lambda to calculate the energy of the light. So notice that's going to take this equation that I boxed out in black here, and that's going to change it just slightly so that we can solve our work function by basically just doing hc over lambda. Okay, so we're just solving for the energy of those 500 nanometer photons, because if we can get the energy of the 500 nanometer photons, and we know that that energy is the perfect amount that we need to eject an electron, then we can use that to figure out basically what that binding energy is, because those values have to match in order for an electron to be able to be ejected. Okay, so all I'm going to do here is put in my values. So H is going to be, whoops, let me switch back to green. H is going to be 6.626 times 10 to the negative 34th joules seconds. C is going to be 2.998 times 10 to the 8th meters per second. And then on the bottom, we want to get 500 nanometers into meters. So don't forget my trick here. If I swap out that nano prefix that I have up top there with the what nano stands for, then I'm going to get 500 times 10 to the negative 9th meters is what 500 nanometers is equal to. Okay, so if we calculate this all out, you're going to get 3.98 times 10 to the negative 19th joules. And we want to remember that anytime we use these equations, these are per particle values. So really, this is the, let me get rid of this actually. Really what we've calculated here is the energy per photon, because we used the energy of the light equation to solve for this. So in this 500 nanometer light, we now know that each photon delivers 3.98 times 10 to the negative 19th joules to the electron in the metal. But since this is the energy that that electron needs in order to eject, this is also representing what the work function value is, right? Per electron, right? They are one and the same in this situation because we're told this is the threshold wavelength. This is the minimum energy we need to get an electron to eject, right? So that is how you want to solve part A of this problem, okay? So what about for part B? So now part B, it says calculate the maximum speed of an electron produced by 400 nanometers of light. So this is basically saying, okay, what if you change the light coming in to be 400 nanometers? Oops. Thinking about this conceptually, note that if we go to a shorter wavelength, right, 400 nanometers is shorter than 500 nanometers, that means we're going to have more energy in the light. So 400 nanometer light should have plenty of energy to match this work function that we just solved for, right? This work function value is this. But that 400 nanometer light is going to have more energy than the 500 nanometer light had. So it has not only the energy to provide for the work function, but it's going to have some amount left over. And so this now means that our velocity is no longer going to be zero when we eject this electron. It's going to have some value based off of how much energy is left over. So for part B of this problem, we now want to remember this relationship again up here between these three energies, because now we do have that kinetic energy term, right? Because if there's enough energy in the light to match the work function and have some amount left over, then we want to use, that information to solve for how much is left over. So I'm going to take this equation up top here and I'm going to rearrange it, because what I want to do is basically solve for the kinetic energy of the light, or of the, kinetic energy of the electrons that are being ejected. So the kinetic energy is going to end up equaling the energy of the light striking the surface minus the work function. Okay? Now, our energy of our light coming in this time is going to use the exact same equation, but our wavelength is different now. It's not 500 nanometers, it's 400 nanometers. So for the first part here, I'm going to put the 6.626 times 10 to the negative 34th joules seconds. I'm going to put the 2.998 times 10 to the 8th meters per second. But on the bottom, I've got 400 times 10 to the negative 9th meters this time, because it's a different wavelength that I'm using in this part of the problem. But since the metal is the same, because this problem started off with giving us information about the metal surface, then that means the work function is the same that I calculated in part A. So I'm going to take this value, the 3.98 times 10 to the negative 19th joules. Oops. And that has one sig fig on it based off of our wavelength here. But I'm going to take that value, I'm going to use that as the work function. Okay, so if we solve these out, I'll go ahead and mention here that the energy of the light term here, let me solve that for us so that we can appreciate what that value is. So I'm just typing this into my calculator. All right, so this energy of this 400 nanometer light, the photons are going to have 4.96 times 10 to the negative 19th joules per photon, right? So that's basically what you get out of this equation. When you type that into your calculator, you'll get this value. So we can see right off the bat here, this number is greater than the work function. So our photons coming in have plenty of energy available to eject the electron and then have some left over. And so if I solve for that leftover amount by subtracting these two, I'm going to get, so 4.96 times 10 to the negative 19th minus the 3.98 times 10 to the negative 19th gives me 9.86 times 10 to the negative 20th joules left over. Now with that value, I can now come back to my kinetic energy equation, which is 1/2 mv squared, and I can set this equation equal to 9.86 times 10 to the negative 20th joules. And basically, I just want to solve for velocity now. Now to solve this, we're going to need the mass of the electron, which is 9.109 times 10 to the negative 31st kilograms. And we're going to have velocity remain as our unit we're trying to solve for, but we can't forget about that square, right? So that's probably the biggest mistake people make with whenever they use this equation is don't forget that that velocity is squared, okay? So to do the algebra on this, the first thing I'm going to do is multiply both sides of the equation by 2 to get rid of this 1/2. So that 9.86 times 10 to the negative 20th value, if I multiply that by 2, I get 1.972 times 10 to the negative 19th joules. And that gets rid of my 1/2. And then I'm going to divide both sides by the mass of the electron to get rid of this. So if I divide both sides, I'm going to divide this value here, the 1.972, by 9.109 times 10 to the negative 31st. And that's going to get me 2.17-ish times 10 to the 11th. And technically units here start to get a little weird because this is like joules per kilogram, but like technically kilograms are part of joules. So that actually ends up eliminating kilograms from the joules units and leaving us in meters squared per second squared. So if you're kind of curious about how those units work out, just remember that joules is equal to kilograms times meters squared per second squared. So if I divide joules by kilograms, right, I'm essentially canceling out the kilograms on top, and that's what's leaving me with meters squared per second squared. Okay, so that equals our velocity squared. And so we're going to get rid of all these squares, right? If you're keeping track of units, you can't make this mistake is really what it comes down to. But if you keep track of all those squares, you're going to note that to get just the velocity, we need to square root both sides. So if I square root that 2.17 value, oops, get this typed in my calculator, I'm going to get about 4.6 times 10 to the 5th meters per second for the velocity. So notice with that problem, you need to recognize the relationship between the 3 different energies. We need to know that we're going to calculate the energy of the light again because now we have a different wavelength coming in. Let me scroll back up to our picture here, right? Different wavelength coming in. It's 400 nanometers now instead of being that 500 nanometers that we used to solve for the work function. So 400 nanometer light coming in, we solve for that energy of that light. We use the work function that we figured out from the threshold wavelength of 500 nanometers. And by subtracting those two energies, we get how much energy is left over that's going to be used as the kinetic energy of the electron. Knowing that that's the kinetic energy of the electron, we just can use that with the kinetic energy equation and the mass of an electron to find what the velocity is. So this is really just algebra at this point, as long as you know which values you're using and trying to solve for. Okay, so all of that is part B. So now this last question for part C just basically involves a slightly different wavelength being used, and it's really just a conceptual sort of question, right? So let me actually let's see here. Let me move my little diagram that I drew up here. Let's move this down to this lower part and talk about how this is going to change. Okay, so if we go back to this diagram here, right? We talked about for part B how if the threshold wavelength for the metal is 500 nanometers, that says that light with a wavelength of 500 nanometers has just enough energy to eject an electron with 0 velocity, right? So knowing your relationship between energy and wavelength, right? And we can think about this with this equation, right? Energy goes up when wavelength goes down, right? Because they have an inverse relationship with each other. So if I put a smaller value in this ratio here on the bottom, that smaller denominator is going to lead to a larger energy. So the smaller the wavelengths are, the shorter that value is, the larger the energy is going to be. So this is why when we moved from 500 nanometer light, which has just enough energy to eject an electron, to 400 nanometer light, which is a shorter wavelength, a smaller wavelength, and therefore higher energy, this is why the electron that's ejected now has some velocity because there's leftover energy, right? So we got this velocity up top here in part B because we know that the light coming in now has more than enough energy to eject the electron, and that leftover energy goes into that kinetic energy of the electron itself, that motion, that velocity. But in this question in C, we're asked now, well, what's going to happen if we change this wavelength coming in to 600 nanometer light, right? So now we've gone to a longer wavelength. So going back to our energy equation, a longer wavelength in the denominator is going to make the energy smaller. So wavelengths that are longer than this threshold wavelength aren't going to have as much energy as the threshold wavelength has. And if they don't have the amount of energy that's in this threshold wavelength, then they're not going to be able to eject an electron. Because remember, that threshold wavelength, that's the bare minimum energy we need to get that electron to eject. If we go to energies lower than that, the electron's not going to eject because we're not going to be able to meet the work function requirement, that binding energy that is needed to get the electron to eject. So basically, when it asks in this question, what's going to happen with 600 nanometer light, right? Like what's going to happen? Are we going to see an electron eject? Are we going to have some velocity? The answer to this question is no electron is ejected, right? We don't see an electron being ejected because this energy of 600 nanometer, the energy of the 600 nanometer light is not going to be enough to eject an electron. Now you should, when you know this material well enough, you should be able to reason this out without doing any calculations. So what I just did there, right, kind of talking myself through it, you should be able to do that. But if you can't for some reason, there is a calculation route available to you, and that just involves solving for what the energy of this 600 nanometer light would be. So if I go ahead and plug and chug all these values again into this equation, and with 600 nanometer light, I'm going to have 600 times 10 to the negative 9th meters on the bottom. And let me calculate this. So 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8th. I get a value of, where'd it go? I get a value of 3.31 times 10 to the negative 19th joules. Okay, so that's your energy per photon for this 600 nanometer light. Let's go check what was the binding energy, right? The work function that was needed for this metal, right? If I come up top here, you may remember that the binding energy, the work function that we calculated was 3.98 times 10 to the negative 19th joules. So let me come back down here and say, right, this work function is 3.98 times 10 to the 19th joules. Do we see how the work function is a larger value than the energy of these photons in this 600 nanometer light? So if those photons don't have this much energy or more, then they can't eject an electron, right? So you can solve this. You can solve for the energy of these 600 nanometer photons and then compare that to the work function and realize it's not going to work, right? This is not enough energy to eject an electron. So that is why in this last problem, it's almost a bit of a trick question, but it's really just, the type of question that's going to be asked to get you to recognize when will an electron not be ejected, right? When do you have the situation where the light doesn't have enough energy to eject an electron? Okay, so that's a really important thing to recognize. And it's also something that you can reason out without doing calculations. As you saw, if you know what the threshold wavelength is, and you have a wavelength that's longer than that, you're not going to be able to eject electrons, because that's just the nature of the fact that longer wavelengths have less energy, and that threshold wavelength represents the bare minimum of energy we need to get that electron to eject.